It asks for maximum acceleration. That's not a common question. Make you go maybe to some places you're not used to. I'm hoping, did you all notice that it wanted to know the maximum acceleration on an interval, on a closed interval? Makes a big difference in your approach. We kind of talked about this a little bit yesterday. Because you're given this closed interval with these endpoints, we're not going to be probably not going to be using any kind of a first derivative or second derivative test strategy. We're going to be testing out the endpoints and critical numbers and determining what the maximum acceleration is. So in order to do that, we need to have an acceleration function. So the acceleration function, of course, is simply the derivative of the velocity function. So 3t squared minus 6t plus 12. And I got to say, maybe you did this. It would be awfully tempting to set that equal to 0, right? But if I did set that equal to 0, like what might be the end result? What would I be finding? Yeah, velocity is maximum perhaps, right? Or minimum maybe. So what I need to do is remember that if I'm trying to maximize something, I have to set something prime equal to 0. In this case, that's acceleration. So A prime is equal to 6t minus 6. That's what I'm going to set equal to 0 to find my critical numbers. And so from that, t equals 1. And then to finish this off, I'm simply going to make a little table for t for an input with acceleration as an output. So 0, 1, and 3 for your candidates. You plug in a 0, you get out a 12. You plug in a 1, and you get out a 9. You plug in a 3, and it's 21, right? Okay. So we're looking for the maximum acceleration. Once you set up a table like this, it becomes very straightforward, right? You say, hey, look, that's where acceleration is highest. And it wanted to know, what the maximum acceleration was. So we'd say max acceleration is or was 21. Happened at t equals 3. Okay. Questions? Any concerns? Johnny?
We don't have any units here?
I don't think so. I was looking through that. I didn't see anything. And of course, if there are no units given, don't make any up. And don't use the whole units per second squared or whatever. Units per time squared.
Distance units per
Make it 21. Yeah. Cool. All right, anybody else? Questions? All right, so we're going to skip a little bit. If you guys would skip ahead to... Which one? Oh, yeah. This one right here, 2003, number 91. 2003, number 91. Or could bring in, I suppose, the fundamental theorem of calculus. So my thought on this one, the way that maybe I would set this up, is to say that the definite integral from 1 to 2 of the acceleration function is going to give me the net change in velocity. Remember the net change theorem? So if you do a definite integral of a rate, that's going to give you the net amount of change. You didn't have to do it exactly this way. I like this way. We could do it another way too if you want, but you'll find that they're really the same way. So I would say that this would equal v of 2 minus v of 1. Remember, the definite integral of a rate will give you the net amount of change of whatever that rate was describing. So then over here, first of all, why did I choose the 1 and the 2? Because I know what's going on at 1, and I want to know what's going on at 2. So v of 2, I want to know v of 1 is 2. And then how on earth are you supposed to find the definite integral from 1 to 2 of a of t? Math 9. So when you did Math 9, I don't know what this came out to be. I bet you, I bet you it's 1.346. 3.3. Oh my goodness, Mr. Butler? Oh.
I forgot that we didn't add.
feeding him misinformation.
Okay. Mr. Butler, you are correct. I thought maybe you forgot to add the 2, but it was actually someone else that forgot to add the 2. Yes, you have the right number. So then you add the 2 over, and you get this v of 2 equals 3.346, right? Okay. Okay. If you wanted to, you could have thought about this a little bit differently. You could have said you know what, I know that kind of like the initial velocity is 2, and you could have said, well, let's go 2 plus the change. 2 plus the change would give you this. And hopefully at some point in here you'd see that this is going to give you the exact same thing, like very quickly. Questions? Again, hopefully this is review and that this is a remembering process versus a I've never seen this before. There's still going to be questions though. All right. So then let's move on to our final one of these. And it was... this one here, the FRQ3 from 2004. It is calculator active. Ready, go.
I bet you were born.
I was born, my brother wasn't born.
God.
So negative
0.133.
negative
I got 0.1329.
0.133.
1.
1329. Okay, fair enough. So I want to make this super duper clear here. There are no units, and so that's not the issue. But if this were an AP test, or if it were my quiz or whatever, and you wrote that for part A, you would get how many points?
Like 1.
None. 0. Yeah.
Not even.
Even that's the right answer. Not even half. The reason is you need to show what you did. And from a very practical standpoint, and I'm not accusing anybody of anything, but from a practical standpoint, it's impossible for me to know if you just took a real quick peek at somebody's paper and saw that number and just threw it down there, or you did it right. I have no way of knowing. The way that you fix this is very, very, very simple. All you have to do is write this. V prime of 2 equals. You might think that that's not that big of a deal, but it's actually a pretty big deal. That tells me that you knew that you're supposed to differentiate V, and then you plug in a 2, and here's my answer. And I know that the calculator did all the details for you. I'm okay with that because the calculator was active. But you must write something that indicates that, yes, I know that I need to take a derivative, and then I plugged in a 2. You write that down, you do math 8, done, we're good, right? Okay, so please be in practice of that. No units needed there. Is the speed of the particle increasing or decreasing at t equals 2? Here you need to compare two things. What are the two things you got to compare?
Sine of the speed and sine of
Not sine of speed, a sine of velocity and sine of acceleration. So I would say v of t, or v of 2, equals something, and a of 2 equals something. Did anybody figure out what v of 2 is?
Negative 0.4.
Give me a number though. Say again.
Negative 0.436.
Negative 0.436. Okay. Anybody figure out a of 2? Oh, yeah, we already had that. There we go. So negative 0.133. All right, so you want to be as specific as you can. You want to show that you're actually addressing this question numerically. So you list those numbers, and as Josh mentioned, they're obviously both negative numbers. And so we could say because v of 2 and a of 2 are both negative, the speed is doing what? Say again? Increasing at t equals 2. Now, questions on B. I find that the concept of speed increasing or decreasing for a lot of folks takes a long time to catch on. And maybe for you it's just stuck with you and it's no big deal. It seems like that's the case. Any questions? All right. Part C, find the time t equals 0, or time greater than or equal to 0, which the particle reaches its highest point. When you see that word highest, what do you think of? Max. Yep, so max height. So we're trying to maximize height. It gives you sort of one endpoint for an interval, right? 0. But it didn't really give you another endpoint. So I'm thinking that probably a first derivative test concept or maybe a second derivative test concept would be the way to go. So if you're looking for candidates for the highest point, what did you set equal to 0?
V of t.
V, right? V of t, velocity. So yeah, you'd want to write this down. And again, just a reminder to you from a how do I communicate this standpoint, if you don't write down v of t equals 0, there is no equation for you to solve. And so if you just magically get this t equals whatever, I got to ask, where'd you get that? And I think I might know, but if you don't communicate it, I don't really know. And maybe you don't either. Or maybe you do. I don't know. So communicate it. Hopefully you used your calculator to solve. If v of t equals 0, t equals how many numbers? Is it just one number? 0.443. Is that, you guys agree? Okay. So 0.443 is when v of t equals 0. Now I'm really hoping this is going to be an uncomplicated question, and at that number, v of t goes from positive to negative? Yes? Okay. So you got the calculator right there in front of you. You probably graphed it to get that number. And so you could probably say v of t changes or deltas from positive to negative at that t value. Therefore, the max height is reached then. Something like that. Do we need to? Did you try it?
Yeah, there was less, but still.
So, but what I'm thinking is with the graph, though, I think you can see that starting at 0 and heading over to that 0.443 number, you've got positive accumulation probably. So doesn't that mean that t equals 0 has to be less than whatever we found there? So I think it's a reasonable thing to consider. But I think looking at the graph, you can say, well, we only accumulated positives, therefore t equals 0 has to be a lower height than whatever that height is.
What is the critical point and then minimum? Like, what would you do?
Then you'd probably go with 0,
Okay.
right? Because then you'd say at that t equals 0.443, v goes from negative to positive, indicating a relative minimum. And then you would see that you'd either, it would be a really bad question, right? Because, like, I peeked over shoulders. Doesn't the graph look roughly something like this?
Other way.
Or other way? Yeah. So it looks like this, right? So if it looked the other way, like what you're suggesting, let's say it did that, I think it would end up being a really bad question. I'd have to give you, I think, an upper bound, because you could look at this and say, you know, that t equals 0 would be the highest point. But the truth is, if you move past this 0.443 number, then all of this is positive position accumulation. And so the maximum is going to be out there somewhere.
Yeah.
And so I think it would just be a bad question.
Okay.
It'd just be poorly designed or poorly worded. Okay, and then part D says, find the position of the particle at time t equals 2. This is another fundamental theorem. And so I would say you could go with something like this. -1 plus the integral from 0 to 2 of v of t. Or, no, it's... You guys okay with this setup? Right, so it's starting position plus change in position gives you that final position, or the position at 2. What number did you guys get for that? -1.06. 361. Okay, so that's the position. You guys all okay with that number? Okay. So then it goes on to ask another question. Is the particle moving toward the origin or away from the origin? What did you use to try to get a sense of what's happening there? Johnny?
I was using velocity.
Okay, so velocity at 2. Okay, so v of 2 we already found, I think, right? Yeah, negative 0.436. All right, so then what would you say based on whatever we've got up there? Is this particle moving towards or away from the origin? Away? Anybody say towards? Okay, so we're saying away from the origin. What's the reasoning? What's the justifying?
Velocity is negative. Well,
And position is negative. You got to say both, right? Just because velocity is negative doesn't mean we're moving anywhere in relative to the origin. What this particle is doing is on the y-axis, when t equals 2, the particle is there, roughly. Wrote that in a bad spot. And it's moving down. So I would say moving away makes sense. We'd say because v of 2 and y of 2 are both negative. Both v of 2 and y of 2 are negative. So maybe a brief, real rough sketch of the graph of what's happening right then would be wise. Guys, any questions? So we're going to adapt this. There's going to be all kinds of things we do with this. Later on in January, you're going to find out that polar is just another version of parametric. And we're going to be asking a really similar question at times. If a particle was tracing this path, would it be moving towards the origin or away? But we'll be doing it in 2D instead of 1D. And it'll be r's and thetas instead of t's, x's, and y's. So, but it's the same concept as far as moving toward or away from some point like the origin. Okay, so if there's no questions, let's do a little bit of vector basics. This is intended to kind of sort of help the folks that maybe have never had physics before, or it's been a while. If you're in physics, or if you've had physics, probably a lot of this is going to be like, okay, really? I did this a lot. That's okay. So, hey guys, hey, thank you. It's just hard to talk when there's a constant murmur. It's just hard for me to concentrate. So, as I've mentioned, in the past we have done a lot of this with a particle. And we just did one of these with a particle. Now we're going to release it to go left and right, up and down, all at the same time. Okay? So it adds a little bit of complexity to it, but I don't think it'll be, certainly won't be beyond you guys. So let's see here. Let's take a look here at this vector here. As you guys maybe know, vector magnitude, like the amount of the vector, is often represented by the length of an arrow. And so I've got this arrow. I've labeled it with V. I've put the little arrow above the V indicating that it's a vector. In our class, we won't be doing a whole lot with the resultant form. We're going to be doing a lot with components. So the way the components of this would work is, would you guys not agree with me that this vector is moving up and right? It's showing up and right motion, or whatever it's trying to describe, in this case, velocity. So I would say that our horizontal component will look about like that. And our vertical component would look about like that. Yes? So we label these in a certain way. One way we could label this horizontal component would be to call it Vx of t. It's the x component of velocity. And then the vertical, of course, would be the y component, so Vy of t. What's key here, of course, is recognizing how you get these things. If we had an angle down here labeled, like maybe we label it with a theta, then that Vx of t would equal the resultant, which is just V, times what? Cosine of theta, yep. And then Vy of t would equal V times sine of theta. So again, just kind of using some relatively basic trig to get these. That's how you would find your components. And so what we're going to be doing, again, just to kind of describe for you guys and make sure that you get the visual here. There's a y-axis, there's an x-axis. In the past, we've had particles that did this, back and forth on the y, or on the x, excuse me, or up and down on the y, something like that. Now what we're going to have happen is the particle is going to be moving around a little more freely. So it's going to be looking like this and maybe like that. It might even cross over itself or not. We could have some path of some particle that looks like that. Go all over the place, and you might question, man, what on earth could make a graph like that? Well, it would certainly be some kind of a parametric, right? And that's the connection here. And some of the things we would do with this is maybe we would want to know the speed at some point, or maybe we would want to know the velocity vector at some point. And so we could find those things at any point. If this was actually the position, we could also find the tangent line equation to the path. Why might that be important? That'll help us actually find the angle that the particle is moving at any point. If you know the slope, it's actually a very easy move there. And then this might not seem like that big of a jump. We could also find the total distance that the particle traveled by maybe finding the length of the curve describing the path of the particle. Does that make sense? So these are all things we've talked about, but we're going to be looking at it in terms of, hey, this thing or this person or particle or whatever is moving around. And we want to know, what is the angle that they're moving at? What is their total distance traveled? What is their velocity? What is their acceleration? Right? All these things could matter. So anyways, I've got some vector basics here. I think I went over a couple of them. Yeah. So that's how you find your components there. And then gravity. So like we might do an example or two in our class. This is not really going to factor into like the AP framework type questions. We might do a question or two in our class where gravity matters. So in feet per second, does anybody know what gravity is? 32. Yeah, 32 feet per second. Should be feet per second squared. 32 feet per second squared is gravity. And then, of course, in metric, it's 9.8 meters per second squared. Or 9.81, I think, if you have more sig figs. Anyways, so gravity might need to be considered in some of the examples we do, but that's not, you don't have to necessarily memorize that. Okay. So really basic vector stuff. How you guys feeling? If you're feeling at all nervous about this, I think when we flip the page over, you'll be like, oh, okay. So we got about 5 minutes left. I thought we'd just talk about a few of the things we'll do with calculus with these. Okay. So when a particle is moving in 2 dimensions, then the direction, the slope, the angle that it's moving, all of a sudden becomes a thing, right? Because when you think about it, when a particle is moving up and down, there's one of 2 directions possible, up or down. If it's moving left and right, it's either moving left or it's moving right. I mean, that's it. But when the particle is moving at some more free 2-dimensional motion, now all of a sudden the angle and the slope are going to be something other than up or down or left or right. That's going to be something we might actually calculate. And so when you look at this, you think, all right, how would we find the slope of some vector-generated curve? Voila, we've done these before, right? In fact, these are going to be on your quiz tomorrow, not in this context, but these will be in there. So the way that you find dy dx is that. The way that you find the second derivative with respect to x is that. These formulas should look exactly the same because they are. Okay? Just some other thoughts as far as what means what in context. So we would say that x prime or dx dt, that's the rate of change of the x-coordinate with respect to time. Just like y prime of t or dy dt, that would be the rate of change of the y-coordinate with respect to time. Or you could think of these two. You could think of these two things right here as simply the x and y components of velocity, right? Those are the x and y components of the rate of change of position, also known as velocity. So notation and physics people, I don't know what you guys have done. I know that for me in my classes that I took in the past and some of the ones that I'm taking now, the vector notation, at least for components, is with these like little pointy parentheses looking things. You guys use those? Or do you guys use I's and J's? So I's and J's are very, very common. But have you seen these at least a little bit? Okay. So we will typically use the pointy parentheses to indicate, hey, this thing is a vector. If you don't have the little pointy parentheses things, you got to use the I and the J to say, hey, this is really a vector. It's got to be one of those two things. I guess there's some others, but those would be the main ones. So again, just some definitions here. This is your position vector right here. This would then be your velocity vector. That would be your acceleration vector. And the way you go from here to here is probably what you're thinking. You simply differentiate once to get to velocity vectors, differentiate again to get to the acceleration vector. So again, all the skills we're talking about are not really new. It's just kind of the context and the fact that now it's 2D motion instead of 1. Okay. Speed, this is where this is a little bit different. If we just have 1D motion, speed is what? The speed function would be what? For 1D motion, speed equals what? Say again, Johnny?
The velocity acceleration.
So I'm talking about, I'm not asking if speed is increasing or decreasing.
The absolute value of velocity.
Absolute value of velocity is it. So guys, listen, this is really huge because you might think that what we're about to look at is very, very different, but it's really not. So remember that when the particle is moving left and right, it's got one of two directions. It's either left or it's right. And we typically designate left as negative and right as positive, right? And so when you absolute value it, what does absolute value do to negatives?
Makes them positive.
And so you're taking away the direction when you do that, right? So the way we do this in 2D motion is we actually take the two components, this one here and this one here. And we actually do the Pythagorean theorem and we find that, remember that triangle we made earlier? We find the length of that resultant vector. We always take the positive version of it, and that's our speed. Hey, perfect timing. Okay, so there's a couple more things we got to go over. We'll do those on Monday. I realize our time is just about up here. So hope you guys have a good day. See you for your quiz on parametric tomorrow. I almost timed that right. Nope.